billions of cold shipments move around the Earth every single year, and we're using sensors usually to keep track of them staying cold or not because they're really important. Think food, think medicine, think biological samples, but the problem there is we generate a lot of e-waste as a result. So on today's episode, we're talking about a wireless tag that remembers overheating without a chip or a battery, meaning that they're perfectly compostable at the end of the day. Hey folks, today on the podcast, we're talking all about the cold chain and the cold chain of logistics that moves lots of cold shipments around every single year. That includes not just food, which is kind of the natural thing that you want to keep cold, but also medical items like vaccines and biologics also need to be kept refrigerated and kept cold while they're moving around. There's billions of cold shipments moving around the Earth every single year. Before we jump into the awesome article we're talking about today, which is about a biodegradable smart sensor, let's talk about the cold chain in general. And this is a technical resource from today's sponsor, Mouser Electronics. We like working with Mouser because they're well connected in the realm of engineering and in the realm of logistics, and they know what topics are kind of on the horizon. They can give you a technical primer on things that are going on. Their technical resources are an awesome way of getting caught up on different technical topics, and today is no exception. They've got an awesome technical resource talking about how the cold chain logistics are important, how there's a need for tight temperature control, and how small swings in temperature can spoil things like vaccine, foods, and biologics. But they also talk about IoT sensors that are used in the cold chain logistics realm. They enable things like real-time monitoring, alerts, predictive maintenance to prevent trucks from failing. And basically the premise here is the more sensing you can use, the better data you have, which means less waste, easier compliance, and more sustainable logistics. And I think it's an awesome, I've said it a couple times, but a primer, a good lay of the land before we talk about the specific solution we're talking about today to try and understand in general what the cold chain looks like and how that has interacted with IoT for logistics in the past.
The breadth of topics that Mouser covers never ceases to amaze me.
I know, man. It's insane.
A little bit of something for everyone. I don't think we've been able to find a topic we've talked about yet where there hasn't been some article or some resource that provides at least, this precursor context to the discussion. So that's awesome.
And in addition to that, a lot of the times it's like, not, spot on with some prediction of the future. And then we're talking about research, cutting edge research that comes out and you're like, oh yeah, the technical resource predicted that. But we'll add this link to the Mouser article technical resource in our show notes. You should check that out as a primer before today's topic, which is a biodegradable smart sensor to help monitor sensitive goods. And this is coming out of EPFL in collaboration with EMPA and CSEM. There's a lot of alphabet soup here, but really what we get is one of the premier technological universities in Switzerland alongside their Materials Institute and one of their institutional centers for electronics and microtechnology. So we've got a collaboration between different institutions in government, different institutions in industry, as well as one of the leading universities in Switzerland. So got a powerhouse team here working on this one.
Yeah, it's really a triple Avenger team assembled. I didn't know. Did you know who these were before the episode? Like, I had to Google them.
No.
EPFL we're familiar with. Yeah. Everyone else, I was like, these sound like cheeses. I was super lost.
The Swiss are known for their cheese.
I know. That's where my mind went.
Yeah. But the premise here, right, is billions of cold shipments moving around every single year. The technical resource from Mouser kind of lays the land of that, of how we're using technology to try and solve some of the issues in the cold chain. The challenge there being that there are tons and tons of batteries and chips getting thrown away right now with the sole purpose of them tracking the cold shipment. And then once the cold item reaches its destination, they're taking the battery, they're taking the chip, and they're throwing it in the trash. And there's a huge e-waste problem due to today's smart labels, which use silicon chips and batteries. They add cost. And one of the problems at scale right here is, like, in 2022, as an example, the world created 62 megatons of e-waste, and over 78% of that was disposed of improperly So only 22% of it is properly recycled. The lion's share of our e-waste just gets thrown into the earth or disposed of improperly, which is a bad thing for us in the long term. So they knew that they couldn't necessarily solve the e-waste problem all in one swing, but they did know that there was some low-hanging fruit for them to keep things like fruit safe with a new type of smart label that doesn't generate any e-waste.
Two things. One, I love how they helped the audience visualize how much e-waste that was by saying it's the equivalent of 11 Eiffel Towers a day for a whole year.
Yeah.
Back in 2022. So it's probably grown since then. Crazy to think about. Second of all, love the emphasis on fruit, given that fruits kind of power the sensor. They're part of the a third of the underlying technology.
Mm-hmm.
So love the point there, Mr. Mitchell.
Yeah, well, let's get talking about it, right? It's a wireless, chipless, printed, temperature-sensitive RFID tag, and there's a lot to encompass there. But wireless, no wires needed to communicate. It's like a sensor that communicates without any type of computer or wires attached to it. It's chipless, which means that there's not technically any electronics on board that can't be disposed of. It's printed, meaning that they can customize it, and that's important. We'll talk about that, why that's important in a second for them to be able to program the geometry of these tags. It's temperature sensitive, meaning that when the temperature around this sensor increases above a certain threshold, the tag physically changes, meaning that you can indicate whether or not something's been kept below its target temperature, or if it's risen above that target temperature to where something was unsafe, you get an easy indication. And one of the cool parts about this is it looks just like a tiny sticker, but it doesn't require any onboard electronics. It uses one antenna, so that's your one piece of electronic. You can use one antenna to read hundreds of these stickers, and you can flag if a shipment ever went above a set temperature, even if it cools back down later. And so the key part here, though, is that there's a lot of other sensors that do that, but none of them right now are completely silicon-free and are designed to be fully compostable. So this is made completely from biodegradable materials. There's no silicon, there's no chip anywhere on this sensor. It is fully biodegradable. It's a biosensor in the purest sense, meaning that there's nothing that's not biodegradable included in the materials list.
Now, we're assuming the audience has the takeaway that by the nature of being like an RFID tag and, it's chipless, you would hope they know that it's not powered. But technically, this thing isn't powered, so there's no battery on board either. The way that these things, quote unquote, receive power is whenever the RFID reader is trying to read them, that signal is enough for them to reflect or refract accordingly, and therefore it is powered so that it can give some signal back.
And this is easiest way of talking about like that reading mechanism, because I was struggling to see how like you could read a tag that doesn't have a chip on it to emit a signal back. They're not technically looking for a return signal that's being broadcast from these things. Rather, what they're looking for is like the resonance at which that that tag rings at a certain frequency. And the way I like to liken it is like if you've ever like yelled in a room with a lot of crystal glasses or crystal chandelier, and you kind of like hear things vibrate in response to the sound waves that you're sending out. It's very similar how this responds. So you broadcast a strong radio signal, and then the tag rings at a certain frequency, kind of vibrates back, and they can measure those resonant frequencies that come back. And one of the cool things about it is if you change the shape of the zinc lines that are printed around on this tag, you change the frequency at which you get the response back. So you can, in theory, print hundreds or thousands of these that are completely unique from one another, and you can indicate which one is the one that got screwed up and got too high of a temperature, or rather which 999 you don't need to care about because they've actually been kept safe.
They're also operating in like the 5 gigahertz band, I think. It's pretty high up there, so they must have a decent allocation. But the other thing I was going to say is this is actually a bit of a full circle moment for you and me, because the way we met was by researching RFID tags for gas sensing. And instead of the resonance frequency shifts, you and I were looking at impedance changes, which is the change in the signal strength as something is sensed. So it's interesting seeing like two different approaches for what is essentially the same problem.
Yeah.
But what's fascinating to me is, like you're saying, obviously you can create the customized antenna patterns for unique IDs, whatever. But in addition to that, you can change the threshold for the temperature at which this activation happens based on, for lack of a better term, the primer or activation material, which can be like olive oil. And that's embedded into these, the composition, let's take a step back. The composition of these sensors is like this biopolymer, the cellulose fibers that have the oil or whatever embedded in it, and then the zinc track that's actually making of the antenna on the chip. And then whenever the temperature goes past a certain point, that oil is then released onto the zinc track, causing this like frequency shift. So based on what temperature threshold you want to set, you can change the oils that you're using to adjust the activation, which is just fascinating.
And it's crazy. So it only happens one way. So it doesn't like have memory of it being hot and then cold again and then hot again and then cold again. But what it can tell you is binary yes, no, was this kept below the target temperature? And if it was above the target temperature at any point in time, these wax pods alongside the side of the circuit that are meant to not melt, that are meant to stay solid, if the temperature gets above a certain temperature, those wax or those oils melt and they start to cover the circuit. And basically what it does is it almost destroys the tag's resonance, or it alters the tag's resonance so that when you try and read that tag, it's not the same as if it was healthy and been kept cold the whole time. So it's got only one time too warm memory is what they call it. Is like it only lets you know once if it's been too warm. It doesn't let you know if it's been too warm 5 or 10 or 15 times. But for critical things that need to be kept cold and you know that they're spoiled or you know that they're suspect, if they were ever above a certain temperature, you can use this for like really, really lightweight, really, really simple one-time sensing. And the way that they tune these different temperature thresholds is by using different mixes of oils. Like you're saying, they talked about using olive oil, jojoba oil, coconut oil, and you can even blend them to get to like the right temperature threshold. But as the temperature gets above a certain level, the oil melts and then it gets soaked into the cellulose layer under the circuit, which changes the way that the signal reflects.
And it's such I love how at the beginning we read off all these institutes, these universities that are like at the top of their game. And the solution they've developed is so beautifully simple.
It is.
It's the epitome of like, what do they say in engineering? Keep it simple, stupid.
Yeah, for real.
You don't have to go crazy with it. You can just leverage existing technology and then be inspired by nature a little bit. And then boom, you have a biodegradable, sustainable IoT tech that can pretty much just save lives. Imagine those vaccines that you no longer have to worry about of, are they good? Are they bad? And then apply to all the other cold shipping products in the world that this can apply to.
And then again, just like going all the way back to what makes these different versus everyone else is cheaper, greener way to check cold chain safety. It's cheaper because there's no active electronics on it. It's also greener because there's no active electronics on it. And so like going back through the ingredients list, the tag is made to be fully compostable, no silicon chip, no battery. Those are the parts that often drive up cost. They're also hard to recycle. They often end up as trash. But the base layer is made of biopolymer / cellulose fibers, which is inspired or directly derived from fruit and plants, which is what Forbode was talking about. The circuit itself is just printed zinc. So instead of using like silicon electronics, it's zinc, which is biodegradable. And then it's covered with a natural wax for protection. And then obviously the temperature trigger are these bio-based oils, so that the end result here is all of the key parts of this thing are either plant-based or biodegradable. The tag is designed to be composted at the end of life. So instead of becoming e-waste, like we talked about this issue where we're generating almost a dozen Eiffel Towers every single day in e-waste, it can be put back into the earth with your apple peel or whatever you're putting it on, or the packaging for these fruits or these vaccines or these biocultures, etc. you can compost these at the end of its life, and it just returns back to the earth. And the awesome solution here is like, it's really, really, really good for a simple yes or no. Was your item in transport ever too warm anywhere during the transportation process?
Absolutely. That was a great summary too. Just nice little wrap up, a little bow on it.
I will say, just like quick, loop it all in, right? We can stop throwing batteries and chips in the trash just to track things that we want to keep cold during the shipping process. The researchers made a compostable RFID sticker that remembers if the package it was on ever got too warm. Doesn't have a chip, doesn't have a battery. It's a printed zinc circuit that rings when it's scanned, and a plant oil on board melts if it overheats. It changes that signal forever, so when you try and scan it again, you know if that item has been too hot anytime during the transportation change. And then you get to scan it and understand, get a simple answer. Has it been kept safely or has it not?
Money. That was sick.
Thanks, dog.
We did an episode at one point with that professor from Harvard, Kit something. Kit Parker. I think they were doing etched graphene tags on fruits instead of plastic labels, which is pretty sick. This kind of reminds me of that, but a more scalable version, because it's much easier to mass produce these RFID tags instead of, individually taking pieces of fruit and then etching on them. So
yeah, well, you can make a sheet of these stickers and keep them on your shelf and then slap them on things when you want to, as opposed to having to print them on the package or on the goods themselves.
Yeah. I don't know. Evolution in the sticker world is always exciting.
Yeah, for sure. And like you said, fun full circle moment for us, given that the first thing we ever worked on together is RFID tags for sensing.
Yeah, almost 10 years ago.
Craziness.
We're old men. All right. Good stuff, man. Solid pod.
All right. Thanks, everyone.